Yeah, greetings, student. Today we are going to look at dyes and natural compounds as our first lecture. And after the lecture, you are expected to know the following objectives. You are expected to define and classify dyes and pigments. You are also expected to give the difference between dyes and pigments. And then finally, you are expected to describe the manufacturing process of dyes, in particular the azo dyes. Okay, so generally pigments are compounds, chemical compounds that are able to absorb light or UV light uh, in the visible range. And when they absorb this light, they are able to produce some color. And these color producing compounds, they have a special name called the chromophore. And it is their structure uh, which gives them the light producing properties. And this structure, it can absorb energy or electrons from source uh, such as the light or from artificial energy sources. And when they either absorb this energy, they can reflect some of the energy. So not all the energy is absorbed. Some of the energy can be reflected. Some of the energy also can be scattered in different directions, whereas some of the energy can be transmitted through. So transmission, there is absorption, there is reflection, then there is scattering. So these are the different ways in which the energy can interact with a pigment or a dye structure. But generally, the color that we see represents the energy that has been reflected. So there is energy that is absorbed, and then that the ones that is reflected is the one that we perceive as color. It is the reflected color that will be captured by the human eye, sending signals to the brain, which we can interpret as color. And then dyes are also organic compounds, which means they have some carbon in their structures, or lots of carbons in their structure, and they are normally used to dye a lot of uh, materials such as paper, leather, fur, human hair, drugs, cosmetics, and so forth. And generally, dyes have been used uh, since the ancient times. For example, in Egypt, the Egyptians, they have used the dyes to dye fabric. They used to embalm dead people or dead kings, whom they called the mummies, and they would dye that fabric in different colors before they embalmed the dead kings. And they tended to use indigo, was a common dye which they used. Also, there's this Tyrian purple dye, which was used by the Romans and which was obtained from snails. And then we have in the mid 19th century, there was discovery of a dye called Mau. It's color like purple color. by a scientist called William Pekin, and he discovered this dye in 1856. And this discovery was very important because it marked the beginning of uh, what we know as the dye manufacturing industry in Europe. Then the Germans and the Swiss, they also began producing some synthetic dyes for the rest of the world during the war, during World War. Okay, and then let's move to classification of pigments or classification of dyes. So pigments can be classified in various ways. For example, we can classify them according to their origin. Some pigments are natural, some are man-made or synthetic, whereas some are inorganic. So you can have inorganic, organic pigments, natural or synthetic pigments. Natural pigments, we obtain them from things like plants, for example, from flowers or colored plants like carrots, tomatoes, etc. All those plants, they are colored. Some pigments are obtained from animals, some from fungi, whereas some are obtained from microorganisms. We have also man-made pigments, and these ones are made by mixing different chemicals in laboratories. And then natural and synthetic pigments are organic compounds. We have said this before, which means they consist of carbon molecules in their structure. Inorganic pigments, they can also be found in nature or they can be produced in labs. Okay, then what is the difference now between dyes and pigments? Okay, so generally, despite them all being colored compounds, uh, dyes are soluble, whereas pigments are not soluble. That's one key difference between these two. The dyes, they form like a permanent uh, structure between the dye and the fabric or the substrate that is being colored, whereas pigments, they do not form this permanent interaction with the fabric. Other key differences are, besides solubilities, in terms of particle size. So dyes have smaller particles than pigments, uh, and this affects their coloring power and also durability of the color. And another difference is in terms of light fastness. So light fastness, we mean how do they resist fading when exposed to light. There are some fabric that can show tendencies of fading when exposed to UV light. But pigments are generally more light fast than dyes. So it means they tend to resist uh, this fading when exposed to light. I think if you look at green plants, for example, uh, they maintain the green color despite being in long hours in the sun. Another difference is in terms of opacity. Uh, and the pigments are usually more opaque than dyes. And then now where do these dyes or how do they form the color? So the structures that are responsible for color formation are known as chromophores. So dyes, they have uh, some groups called chromophores, which are responsible for their color formation. And as you can see, some examples of the chromophores are shown there. And they normally are groups of carbon-carbon double bonds or carbon-carbon triple bonds or some electron-rich phenolic groups as shown on the screen there. So it is these chromophores that have some light absorbing capabilities, uh, and these groups are called chromophores. They are able to absorb radiation from the light in the visible region from 400 to 700 nanometers. So groups that have lots of these chromophores or molecules that have lots of these chromophores uh, are able to produce what? A color. And some molecules have special arrangements of these carbon-carbon bonds. For example, vitamin A, it has what's known as a conjugated system, a system that has alternating regions where there are double bonds, okay, as seen on the screen there. See that there is a region with a carbon bond here, followed by another region without carbon bond, then carbon bond, no carbon bond, carbon bond, no carbon bond, and so forth. So systems that have this conjugation system, they are also able to produce color. And then the third aspect about color production is the presence of groups that are known as oxochromes. So these groups are responsible for uh, slightly altering intensity of the color. I'm sure we know that we have different shades of color. We have deep green or dark green, light green, and so forth. So oxochromes are responsible for changing the light intensity. And the examples of oxochromes are shown on the screen there, things like the hydroxyl group or the amine group and so forth. All these groups are oxochromes. So in essence, dyes or dye molecules, they possess a conjugated electron system, as was shown there. It is this system that gives the dyes the ability to absorb light in the visible region of the light spectrum and hence giving out color. So a compound that contains a chromophore is known as a chromogen. And then we have uh, additional groups on chromogens, which are known as oxochromes, the ones which I said are responsible for color intensity. And then we also have another special dye called the azo dyes. They contain this linkage, N linkage. This time it's not carbon linkage, but it's nitrogen linked by double bonds. And they form uh, what's known as the azo dyes. And this group is called the azo group. The N double bond is the azo group. And a typical example of this dye is known as azobenzene. Okay, okay. And so where do color comes from? I mean, we have different colors, but the visible spectrum contains the colors violet, blue, green, yellow, orange, and red. And light interacts with matter in different ways. Like I said before, light can be absorbed or can be reflected. some light can be transmitted through, which means it's passing through from through a substrate and it goes to the other side, or it can be absorbed, which means it gets inside the substrate and doesn't pass through, but it gets absorbed. And then sometimes light can be reflected, which means it's bouncing off from a substrate. It hits a substrate, some light gets reflected, and sometimes light can be scattered, which means it bounces off a substrate in different direction. So if light is is reflected, we perceive color as white. Okay. Then if all the light is absorbed, we perceive the color as black. So that's why maybe it's common for people to say black clothes are hot and so forth. It's because of this capability of absorbing all the wavelength of the light. So it the there's that perception of heat because there's absorption of all the energy or all the wavelengths of the light. And then when light is completely transmitted through, we we see or we perceive the light as colorless. It will be colorless. So that's the different ways, or that's the different color options that we have. There's uh, black, white, or transparent, or colorless. So where do the other colors come from now? The other colors, they come from the point that, or the fact that some substrates now, they can absorb some and reflect some light. Okay. Remember, we were saying when all the light is absorbed, that's when we see black color. But some substrates, they have the capability of absorbing some portions and reflecting some portions of light. So that's where other colors come from now. It is the portions that are reflected which give the other color options. For example, red, violet, blue, green, etc. They will be reflecting the portions of color that have been what? That have been reflected. Okay. And when light is uh, absorbed by a molecule, the energy it is absorbed by electrons, and electrons they gain the energy and they get excited and they then move from ground state to an excited state. Okay, so there's that movement of electrons in from the, if you remember the shell structure, the shell structure. So there's that movement from ground state to what? To the excited state because the electron has gained what? Energy. Okay. So if the difference between ground state and excited state, which is known as the valence, if the difference between ground state and excited state of a molecule is greater, it means that that molecule needs more energy to move its electrons from ground state to excited state. But if the distance between ground state and excited state is lesser or is shorter, that molecule needs less energy to move its electrons from ground state to excited state. So molecules that are rich in these conjugated systems, the ones I talked about earlier, those with the conjugation, okay, they need less energy to excite their electrons because the valency is very short. So that's one property you need to know about conjugated systems. So they just need just a small amount of energy to excite what? Their electrons, the conjugated systems. But molecules without conjugation, they need a lot of energy to excite their electrons. And the conjugated system, it will absorb the lower light part, the UV spectrum. Remember, we said that the the spectrum, it stretches from about 400 to about 700 nanometers. Okay, and with the spectrum now, the the lower the number, the greater the energy. So as you can see, the violet region, 400 to 50 nanometers, is the high energy region. Okay, then the higher you go, like if you go to 700 nanometers, it means that that wavelength is low energy. So we have short wavelengths and high wavelength, or a long wavelength. Short wavelength is high energy wavelength, like violet, whereas uh, long waves, those with 700, 600 nanometers, they are uh, wavelength with less energy. Okay, so conjugated systems now, they usually absorb the long waves, these ones, yeah, ones with less energy, because they just need small amounts of energy to excite their electrons. Then they reflect the other high energy region, and it is the reflected energy which we see as color. So for conjugated systems, we normally see the colors as is violet, blue, or green, because it is the energy that is reflected. Conjugated systems, they just absorb this less energy region and reflect this other part. Now, non-conjugated systems, they need high energy because the valency between the ground state and the excited state is quite big. So they will absorb uh, a lot of high energy, uh, like violet and blue, and reflect the other low energy uh, wavelength. And so we see the reflected uh, energy, yellow, orange, etc. Okay. So I may ask, pose a question to say, the green color in green plants, which color do they absorb, and which color is reflected? The color that is reflected is the color that we see. It is the green. So which color is absorbed? The color that is absorbed is the complementary color, which is red here. So we see the complementary color. And as you can see on this color wheel, green is complementary to red, violet is complementary to yellow, blue is complementary to orange. So if a molecule absorbs blue, it will reflect orange. If it absorbs violet, it will reflect yellow, and we will see yellow. So green plants, they absorb red, or they absorb the energy between 640 to 700 nanometers, and our eyes will see what? The complementary color, which is 480 to 560 nanometers, which is green. Okay, so that's why we see some portions of light being absorbed and why some are seen as are not absorbed. It's because of the conjugated system, and it is because of the difference between ground state and excited state of different molecules. Some molecules have uh, less valence between ground state and excited state, whereas some molecules they have high valence or high distance between ground state and what? And excited state. And the differences between the valences now determines how much energy will be needed to excite the electrons. Okay. And then we move to classification of dyes. So dyes are classified in various ways, for example, according to their structure or according to the method by which they are applied to substrate or the material. The substrate is the material which is being colored. For example, leather, wool, hair, etc. So we have various uh, dyes, for example, acid dyes. Okay, this classification is based on what? On on chemical structure. So we have acid dyes, also have the basic dyes. They are also known as cationic dyes, whereas acid dyes are also known as anionic dyes. We also have the direct dyes. We also have azo dyes or azoic dyes. We also have nitro dyes. We have disperse dyes, reactive dyes, sulfur dyes, VAT, and so forth, many more. Okay, and you are expected to know the different uh, classes of these dyes. So acid dyes are dyes which contain acidic groups in their structure, and most acidic dyes they contain what's known as a sulfonic group. This SO3H group is a sulfonic group, and as you can see, this dye has this group, the NN group, which I said is called azo group. So there is this dye has an azo group, but at the same time, it is also an acidic. It is also an acidic dye, and it's known as acid yellow 36. Okay, and acid dyes they are common in wool and nylon, and the anionic group, which is this acidic group, it interacts to negative portions uh, to positive portions, I mean, of the fiber. Okay, because we said these acidic dyes they are also known as anionic, and anionic groups are positively charged what groups. So the positive part of the dye it interacts with the positive groups on the fiber. The negative part of the dye interacts with what? With because SO3, it's SO3 minus SO3 minus. So the fiber now, let's say this is the fiber. For it to attach to this dye, it has to have some positive groups. It must have what? The positive groups. And these positive groups, they can interact in an ionic bond. So it means they displace this H plus here. We have H plus and the fiber now comes and forms an ionic interaction with the dye. So acid dyes, they have the SO3 minus group, okay, which then interacts with the positive groups on the fiber, resulting in some ionic bonding between amino groups and the sulfonic groups on the dye. So you need a fiber that has some positively charged groups or cations, for example, NH3 plus, H3 plus groups. It is these amine groups that can react, that can form an ionic bond with the SO3 groups. Okay. Then we also have some basic dyes or cationic dyes. These ones are opposite of the acidic dyes in the sense that these ones now, in their structure, they contain amino groups, which means the dye contains some negatively charged groups like amine, NH2. Okay, so they are mostly amino or substituted amino compounds, and they are soluble in acid. Okay, and they become attached to fibers by formation of ionic bonds with anionic groups in the fiber. So this time around, the fiber must have anionic groups or positively or negatively charged groups like SO3 minus, like SO3 minus groups. And the SO3 minus groups then interacts with the amine group in the dye. An example of a basic dye is basic brown one. Okay, which is shown here. This is basic brown one, and you can see these amine groups uh, is one, two, three, about four. And again, it also has an azo group. You see, this see this conjugation is through the azo group. We also have basic violet 3, okay, and this time it's a substituted amine group. In place of NH, N here, then in place of NH2, this time you see that it has been substituted with a CH3, so it's called substituted amino group. We also have a basic blue 21 here. Again, it's a substituted amine group. Then we have direct dyes. These are water soluble anionic dyes, which means they are like acidic dyes. But then what's the difference between a direct dye and an acid dye? The difference is that whilst the acid dyes, they use the acidic group to join or to connect with the fiber. The direct dyes, they do not use acidic groups as a means to attachment to the fiber. That is what's the difference between acid dyes and direct dyes. They don't use their acidic groups to connect to the fiber. That's the difference. Okay. Most of the direct dyes are what are known as polyazo compounds. So they have many azo groups, these N groups. Okay. And the solubility of these dyes is often reduced by adding common salt, our sodium chloride, or what's known as globular salt. Okay. Example of a direct dye is direct orange 26. and these dyes are commonly applied to cellulose fibers. Okay, and then also have azo dyes is another class of dyes. The azo dyes, they contain this uh, nitrogen group, which is connected to the double bonding, and this azo dye connects some aromatic rings. For example, if we look at the bluish red azoic dye, we have NN connecting two aromatic. This part, also this part, are connected through this what? Through this azo dye. Then we also have nitro dyes. Nitro dyes are dyes that contain NO2 group. Example is picric acid. So they have this NO2 group, but they also contain additional groups such as these oxochrome groups. And remember what we said are also oxochromes. Oxochromes are groups that can modify the color intensity of the dye. So it is NO2, 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 but it also contains an oxochrome group here, the hydroxyl group. It's one of the oldest nitro dyes, picric acid 2,4,6 trinitrophenol. We also have the dispersed dyes, and these are not soluble in water. And example is dispersed blue 79. Again, it has this azo group, okay, and they are used for polyester and acetate fibers and so forth. We have other groups of dyes which you can go on and read, such as these reactive dyes, sulfur dyes, also have fat dyes, uh, fiber reactive dyes, mordant dyes, etc. For example, mordant red, etc. Go on and read all these other groups of dyes. Okay, and then there's a table here which shows some various applications of dyes. To say acid dyes, where are they commonly applied? So acid dyes are common in nylon, wool, silk, paper, and so forth. Whereas the azo dyes are common in cotton and rayon, etc. Okay. Then we also have the pigments. We also have the what? Okay, then we also have in pigments. We have talked about dyes, but we now talk about pigments. And just to recall, we said the key difference between dyes and pigments is that the dyes are soluble in water, whereas the pigments are non-soluble. And also in terms of particle size, that's also another key difference, where we said the dyes have smaller particles when compared to what to 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 pigments and so forth. So most pigments are natural and they are obtained from plants and algae. Okay. Example is the chlorophyll, which we see in green leaves or green plants. Also have carotenoids, which are common in carrots If you see the yellow color in carrots, it's typical carotenoid. We also have the anthocyanins, and all these are types of what? Natural pigments. But we also have some aquatic uh, organisms such as algae and phycobilins. They are also important pigments. The algae have different color pigments like green, red, etc., yellow. So in terms of the pigments, we have the anthocyanins, which are polyphenolic compounds that have two aromatic rings, which are bonded by a carbon 3 unit or a central pyran ring. Okay, and it is this ring which is known as the central pyran ring. This ring. Okay, that's what the central pyran ring. And all anthocyanins are what? Flavonoids, which means they contain this oxygen group. That's what it means. They have this what? Oxygen group here, the flavonoids. And they are soluble in water, and they produce different colors in petals of flowers or fruits, etc. And then we also have carotenoids, and the carotenoids they exhibit yellow, orange, red, purple colors, etc. A carrot plant or fruit is an example of the carotenoid. We also have beetroot. The beetroot, a vegetable, is also a carotenoid. Okay. We also have the naphthaquinones, and they have this structure. And then we also have the anthraquinones. Okay. Then we have melanin. Melanin is the skin pigment, the black pigment in our skin, or it's also common in hair and also in nails. So it's responsible for giving black, gray, or brown color to animals, plants, and also to microorganisms. Okay. And then we have dyeing process. And the dyeing process generally it proceeds according to the following sequence. So the dye moves to the substrate, then the dye is absorbed by the fiber or the substrate. Then there is diffusion of the dye into the fiber of the polymer. Then there is retention of the dye in the substrate. And the dye is retained through different ways of bonding. For example, ionic, covalent, entrapment, hydrogen bonding, and so forth. And then in terms of manufacture of dyes, you can typically see a typical flow diagram which shows manufacturing process of a dye. We have raw materials which are then fed in reactors. Here the dye and substrate react through various ways, and there is attachment of the dye to the fiber. Then after that there is filtration to remove unreacted dye and other unwanted substances. Then we isolate the product. Then there is grinding, there is drying, grinding, or what, or milling. And a typical process in the manufacture of dyes, which is common, is the manufacture of the azo dyes. The azo dyes, they represent one of the most important groups of dyes, and many hundred of commercial dyes are azo dyes. And we said the azo dye, they contain this uh, nitrogen group, the azo group, which joins two or more aromatic rings. And how are the azo dyes manufactured? It involves uh, a diazotization process where a primary aromatic amine is diazotized to form a diazonium salt. And then this diazonium salt is then coupled with hydroxy or amino derivatives of aromatic hydrocarbons. And the step involves diazotization first, there is coupling, there is then isolation or filtration, drying, grinding, and standardization. So typical process includes the first step, which involves nitrosation from primary aromatic amine. So here we want to introduce amine groups to the aromatic amine, to the aromatic structure. We want to introduce an amine group, which is NH2. And this is done first by reacting a strong acid like HCl with sodium nitrite, as shown in the first reaction. Sodium nitrite plus HCl at temperatures less than 5 degrees Celsius, and we form this HNO2. This HNO2 now will then react with the aromatic group to form a primary aromatic amine, which is this one, is this NH2, then the aromatic. And then if we further react the primary aromatic amine to nitrous acid, this is the next step, which is known as diazotization now. And if we react then this primary aromatic amine with nitrous acid in acidic environment, which means in the presence of hydrochloric acid at a temperature below 5 degrees Celsius, we form what's known as a diazonium salt. For example, in this case, we have benzene diazonium chloride. And the structure of a diazonium salt is as shown here. It has this group N triple bond N. And then this first N group is positively charged, whereas this part is negative. So it's like a salt because it has positive and negative uh, regions in its structure. So it's a diazonium salt. And in this case, the salt is formed with a chloride. But you can have others like fluoride or iodide, etc. And then this diazonium group now will then go to the next stage, which is coupling. And the diazonium salt can also be shown using this format, this one. You say R, then R to represent this part, then N plus, then N. That's the diazonium salt. And the next stage in the manufacture of diazo dyes is the coupling reaction. By coupling, you are reacting the diazonium salt to an electron-rich compound. For example, phenol here. It's a electron-rich region. So it's an electrophilic substitution reaction. So the diazonium salt, it attacks the electron-rich region. So it reacts in an electrophilic substitution reaction. As you can see, this diazonium salt attacks this electron-rich group, and it then forms this compound. And this compound, it's a diazo. It's an azo die because it is an azo group connecting two aromatic groups, one to the left and one to the right. It's a diazo die, and it's called known as 4-hydroxyphenyl azobenzene, and it's bright orange in color. So formation of or manufacture of azo dyes includes first step nitrosation, where we form this primary amine if we don't have it already. Then the next stage is diazotization, where we form the diazonium salt. And how do you form a diazonium salt? You react a primary aromatic amine like this one. You react it with nitrous acid in acidic environment and at temperatures less than 5 degrees Celsius. You form this diazonium salt. Then the next stage is coupling, where you react this salt to an electron-rich compound like the phenol. And this reaction is a electrophilic uh, substitution reaction, where the diazonium salt, because of this plus charge, it's an electrophile. It is attracted to electron rich regions. So it attacks this, and the groups are then connected through an NN bridge, this bridge between these aromatic rings to form a dye. And the dyes, these other dyes are commonly used for fabrics, food, or as acid-base indicators. Okay, and these are some of the common azo dyes here. Okay, yeah. So in summary, this has been a lecture on what on dyes, where we learned uh, about dyes and pigments. What are dyes? What are pigments? How are dyes classified? We said according to chemical structure, or according to how they are used. We learned about the different classes of dyes. Examples being the acid dyes, also known as the anionic dyes. We have the basic dyes, also known as the cationic dye. We also have the direct dyes, art dyes, and many other uh, types of dyes. We also learned about the color formation, uh, where dyes uh, get their color from, or where color originates from, where we talked about the conjugated electron system, the chromophores, oxo, oxochrome, oxochromes, and also chromogen. Then finally, we looked at the manufacture of azo dyes, where we said it's a process which involves the nitrosation or formation of primary aromatic amine, which are then used to make diazonium salts by reacting the primary amine with nitrous acid. Then this diazonium salt is then coupled or connected to an electron-rich aromatic group, such as phenol, to form compounds such as these ones, which are aromatic groups connected with an azo bridge or an azo group. Okay, so thank you. We'll meet in the next lecture.